According to the International Maritime Organization, passage planning has 4 elements: appraising all relevant information, planning the intended voyage, executing the plan taking account of prevailing conditions, and monitoring the vessel's progress against the plan continuously. The coastal navigator must monitor the progress of the boat along the planned route. The boat's position should be recorded frequently, using a variety of methods including position lines from GPS, transits, compass bearings, radar ranges and sextant angles. A navigator should be periodically checking the echo sounder readings during the voyage. The frequency of the checks should increase as the underkeel clearance decreases. After taking the bearings, the boat master has to plot them on the chart. The position line or useful portion of it near the vessel's location is drawn from the charted object in the direction opposite to the bearing, the reciprocal bearing. The boat master understands that the bearing is taken from seaward, but, on the chart, the position line is plotted from the object. On this slide, the navigator, on passage between Port of Spain and the Grand Boca, took compass bearings of 2 charted objects, the light at the east end of Gaspar Grand and the light on Nelson Island. He also has the transit provided by the radio mast on Point Goward and the light on Kronstadt Island. The spread between the bearing lines is close to the ideal right angle, 90 degrees, that minimizes the position error resulting from small errors in taking and plotting bearings. The navigator should avoid using fixes where the position lines intersect at less than 30 degrees, unless no better lines are available. In navigation, the bearing of an object is the horizontal angle between the direction of the object and another reference object. The reference object could be the true North Pole or the magnetic North Pole, for true or compass bearings. It could be the angle between the object and the bow of your boat for relative bearings. It could be the angle between the object and what the gyro or radar thinks is north for gyro and radar bearings. Only true bearings can be accurately plotted on nautical charts. This is one of the reasons navigators should be obsessed with compass error. We know we have to constantly check if there are differences between the output of devices used for taking bearings in true north. Ranges are distances in navigation. A line connecting all the points 5 miles from an object will be a circle around the object. In navigation, we use the part of the circle closest to us. Radar is an acronym for radio detection and ranging. Radar emits a short burst of electrical energy through a highly directional antenna and, by measuring the time lapse until the signal bounces back to the receiver and noting the position of the rotating antenna, translates the result to the range and bearing of the target. Radar is used for measuring the distance from an object observed at sea for collision avoidance and position fixing. The navigator must consider the limitations of the equipment in use. Among the things he should take into account are that radar is more reliable for ranges because of its principle of operation. These steep cliffs on Shakashikare Island are radar conspicuous. Here are the cliffs of Shakashikare on the nautical chart. Navigators should consider the ranges are likely from shorelines and lighthouse may not be on the shoreline. This chart extract shows the difference between a cliff coast and a lighthouse. So measure the range from the cliff, not lighthouse. A beach coast is less radar conspicuous, and navigators must be aware of the reduced accuracy of the position line. Radar is less reliable for bearings because of distortion of detected objects. The Global Positioning System, GPS, is a space-based satellite navigation system that provides position information anywhere on Earth where 4 or more GPS satellites are visible to the receiver. Visible means above the horizon and unobstructed. In 2015, there were 30 operational GPS satellites with another one being commissioned. GPS satellites orbit Earth twice per day and transmit information. GPS receivers compare the time a signal was transmitted by a satellite with the time the signal was received. The difference tells the GPS receiver how far away the satellite is. The GPS receiver does this for the 4 or more satellites and calculates the antenna's exact location and displays it either on the unit either as coordinates or on the electronic chart. Even the most expensive electronic devices are susceptible to malfunction occasionally in the hostile marine environment, and the boatmaster has to be thoroughly familiar with the electronic equipment while remaining familiar with the conventional position fixing methods, for example using transits. He must be vigilant and not over-reliant on the electronics. Deduced or dead reckoning is the process of estimating the position of a boat based solely on speed and direction of travel and time elapsed since the last known position or fix. So all you need to figure out approximately where you are is a speed indicator like a log, a clock or watch, and a compass. Dead reckoning does not use position lines, so it is different from navigation by visible landmarks and celestial navigation. Since the development of radio technology, various forms of electronic navigation have also been developed, the best known of which is the satellite-based global positioning system. Navigating by external reference points is more accurate, but dead reckoning is the fallback when all else fails. The deduced reckoning position does not take current into consideration, but there is current in the real world. The line from the initial position to the docked position is called the water track. There is current information in nautical charts and publications to help us predict the current in our vicinity. We can then apply a current vector at the end of the water track. This is the line that represents the direction and distance the current has moved in the same period. The tidal vector has 3 arrows and the ep is indicated by a triangle around the position. An ep should also have the time and log reading of the time it was plotted. Buoys are shown on charts slanting to the right, at an oblique angle. The letters and numbers used to describe the colors and characteristics of the buoy are also slanting to the right, in italics. The charted position of the buoy is the small circle at the bottom of the symbol. The use of floating buoys for position fixing should always be done with caution. Buoys are floating and held in position by a chain connected an anchor on seabed. Poorly installed and or maintained buoys can float to one side then the other side of its charted position, the anchor as the tidal current changes from ebbing to flooding. In strong currents the buoy can sometimes drag its anchor out of position. The end of the chain near to the anchor chafes on itself and on the seabed and can break, resulting with the buoy drifting significantly out of position. For these reasons, the use of buoys only for position fixing is not advised. Beacons are based on piles driven into the seabed. Beacons are shown on charts upright and the letters and numbers used to describe the colors and characteristics of the beacon are also upright. The charted position of the beacon is the small circle at the bottom of the symbol. Beacons usually provide more reliable position lines than buoys, but note that the P next to the Soldado Rock beacon tells us a charted position approximately. Position lines from Soldado Rock should be treated with caution. These are photos of a Spolin light on Gaspar Grande, on the left, and the light on Gasparillo Island. It could be that these lights are obscured from some directions because of the overgrowth of bushes. The usefulness of fixed beacons for position fixing depends largely on the condition of the fixed beacon and how well maintained they are. It is a mariner's duty to report the condition of aids to navigation to relevant authorities. A transit can be created by any two charted features that are in line, such as a fixed aid to navigation in line with the high point of an island. The boatmaster may observe a buoy aligned with the structural shore and create a transit. A straight line through both objects on the chart can be plotted without requiring the actual compass direction. The boatmaster should be constantly thinking in terms of transits for reliable position lines that are independent of shipboard equipment that might be faulty. Leading lights are two or more lights deliberately situated in a line, forming a transit ashore. These lights, when in line, provide a position line indicating that the ship is in the safe part of the navigation channel. The light that is closer to the coast is called the front light and the light that is more inland is called the rear light. The rear light is usually higher than the front light. Sometimes the lights are synchronized. The front leading light for the Sea Lots channel is on the chart as occulting 10 seconds, 26 meters, 6 miles and fixed, red, and the rear leading light is flashing 2 seconds, 39 meters, 6 miles and fixed red. The FR means fixed red lights, so both front and rear have synchronized red lights. The front light is 26 meters high and the rear light is 39 meters high. The white lights are not synchronized. The front light is occulting every 10 seconds and the rear light is flashing every 2 seconds. The sextant can be used on the coast to measure vertical sextant angles that yield a distance off a charted object. The sextant can also be used to measure horizontal sextant angles between charted objects to get a position line.